My name is Ken Wolf, and I'm the president of the Aerostar Owners Association. I'm not a professional pilot by trade, but I'm certainly an avid Aerostar enthusiast. This video presentation today is designed to offer practical, safe operating information which should help the new Aerostar pilot safely transition to his or her machine. It should also offer the experienced Aerostar pilot not only a basic review, but alternative methods and tricks, if you will, to get the job done more safely and expeditiously. This video has been reviewed and edited by more than a half a dozen very experienced Aerostar pilots. Nevertheless, it does contain personal opinions, and therefore, the Pilot Operating Handbook must always be the guide to safe operating practices. The Aerostar outperforms all other piston twins and even some of the turboprops. It does, however, have some design characteristics quite different from all other aircraft. Thorough knowledge of the aircraft systems is absolutely mandatory in maintaining and flying your machine more safely and efficiently. I'd suggest viewing previous AOA tapes which cover these systems in great detail, as well as a thorough review of the Pilot Operating Handbook for the Aerostar. This tape, however, is about flying the Aerostar, so let's get started.
The complete pre-flight has been covered in one of the previous AOA tapes, so we'll only highlight a few areas. First of all, like all high-performance pressurized turbocharged aircraft, the Aerostar requires attention to good operating practices. This complex aircraft absolutely demands the use of a checklist, and to fly without one is to risk forgetting a critical item. In addition to checking that the fuel and mags are off prior to pre-flight inspection, the operator should bleed off the hydraulic pressure by sequentially lowering and raising the flap until there is no more pressure in the system. By doing so, the pilot can ensure that the accumulator is properly charged, as evidenced by a rapid drop of pressure to zero, commencing at approximately 500 psi. Depleting hydraulic pressure also allows the main gear doors to be gently pulled open an inch or so for interior inspection during pre-flight. With the hydraulic pressure completely bled off, the pilot can accurately read the fluid level in the hydraulic reservoir during pre-flight. Checking the fluid level with the hydraulic system pressurized gives a low reading, and adding hydraulic fluid based on that reading will result in overflow of the reservoir when the system is depressurized. Finally, depleting hydraulic pressure will later allow for testing the auxiliary hydraulic pump during the startup procedure. Always carry a flashlight on pre-flight inspections, whether it be day or night. There are many nooks and crannies which can't be adequately inspected without one. These include nose gear wheel well area with steering actuator and steering collar, main wheel well areas with gear door valve, hydraulic lines, gear door linkages, and the snubber cylinder to hold the door tightly closed, landing gear struts for leaks, and the strut retract area with the main gear actuating cylinder and gear position switches, air inlet areas in front of engines for viewing the top cylinders, plugs and leads, fuel lines to the cylinders, air reference lines to the fuel injectors and the cooling baffles, exhaust area for viewing the underside of the engine checking for fuel, oil, or in the case of right engine hydraulic leaks. A flashlight is used to view behind the baggage area for any hydraulic leaks, as well as checking the heater and air conditioner for general integrity. Check under the wings for evidence of fuel stains from leaking rivets. In doing your walk-around, check the ground under the wings, fuselage, and for fresh liquid or stains on the ground as a clue to engine or airframe leaks. Here are a few more pre-flight tricks. Shake your tailpipes vigorously before each flight. Slight sideways motion is permissible, but any vertical motion of the pipes is an absolute indication to cancel the flight and investigate for possible loose or broken turbocharger support brackets or a broken tailpipe. When checking the oil level, don't leave the oil dipstick in the spinner where you can easily forget it. Put it lying down in a position to prevent closing the oil access door. Except for extended flight, fill the oil level only to 9 or 10 quarts to avoid blowing oil overboard and messing up the wings and fuselage. An optional breather kit allows the operator to fill the sump to its full 12-quart capacity. When fueling the aircraft, always fill the center fuselage tank first, since it's the only tank which reliably delivers fuel in all flight attitudes. Additionally, fuel as needed is then added to the wing tanks. Always fuel just before departure to prevent wing tank pressurization and consequent fuel leaks. Be aware that fueling to 1 inch from the filler neck will prevent wing tank pressurization and leaking rivets caused by expanding fuel, assuming the wings remain level. But if a strut drops or the aircraft is pulled away from the pumps and parked on an uneven surface, the wing will drop and the fuel level will rise and shut off the float valve, causing the wing to pressurize. Also, be aware that a flight conducted with full fuel, which lasts less than 1 hour, can still leave enough fuel in the wing tank to close the float valve if the aircraft is parked on an uneven tarmac with one wing low. A wing with only 50 gallons in it can close the float valve if the wing is sitting in a 3-degree low attitude. A service bulletin to improve wing tank venting is now available and eliminates all of these concerns. Flights, to ensure completely filling the wing, bump up the wing at least 1.5 degrees using a protractor. This will prevent trapping a large air bubble in the tank with consequent reduced fuel load. To save your back, let gravity help in the bumping procedure as follows. Fill one tank to 2/3 full. Then bump the second wing up, letting the weight of the fuel in the opposite wing tank aid you. Now completely fuel the second wing. Ensure that the wing is up 1.5 degrees at the end of the fuel loop. Now bump the wing with 2/3 fuel in it, using the full fuel from the wing you filled as a counterweight to help raise the 2/3 filled tank. No broken back that way. Don't break the wingtip either by applying force on the fiberglass wingtip extension. Bump at the spar location at least 2 feet in from the wingtip to prevent damage to the fiberglass wingtip extension. Some pilots fill the tanks to the filler neck before departing and leave the fuel cap locking tabs up to prevent pressurization while they finalize preparations for departure. A checklist item or a streamer reminding the pilot to confirm that the tabs are down and locked will prevent a takeoff with fuel siphoning overboard and fuel failing to feed from either wing tank to the engines due to negative pressure created over the open cap while in flight. Obviously, leaving the fuel tabs up with possible inclement weather sets the stage for water contamination of the fuel should rain develop. While it's possible with various fueling techniques to load a total of 174.5 gallons in the center fuselage and wing tanks of an Aerostar, the Pilot Operating Handbook mandates that only 165 be considered usable. An uneven tarmac, unequal struts, or differential tire pressure can result in the wings not being level and consequently not being completely filled at the time of fueling. Therefore, only 165 is programmed into the fuel flow totalizer. As a consequence of this conservative fuel quantity entry, during flight, the fuel gauges may show up to 9.5 gallons more fuel remaining than is displayed by the fuel flow totalizer. Safety dictates that the lesser number be utilized for range considerations. Also, be aware that the heater uses 0.6 gallons per hour, or roughly 3 gallons of fuel over an extended cross-country flight, which is not detected by the fuel totalizer, but will be reflected in the fuel gauge indications. This is another reason to be conservative in the amount of fuel entered in the fuel totalizer before flight. There's a safe and orderly manner for loading passengers in the Aerostar. First, push the pilot seat full forward and the co-pilot seat rearward, and then assist the right front passenger. His seat is then moved forward, making room for rear seat passengers to enter. The pilot enters last and visually checks for closure of the baggage door before entry. His seat should remain back until he's viewed the 4 safety pin indications showing that the main door is securely closed. While the factory-installed seat stop will prevent the pilot seat from sliding rearward, an extra removable seat stop will prevent the seat from sliding backwards more than an inch in the event of a failed seat lock mechanism. Elements of particular interest to the Aerostar pilot in the pre-start routine include ensuring that the gear handle is down before turning on the battery master switch. If not, the nose gear will retract with damage to the nose of the aircraft as it settles on the ground when the electrical system is energized and the aux hydraulic pump pressurizes the gear retract mechanism. With the gear handle checked in the down position, the pilot can safely turn on the battery master. And with the auxiliary hydraulic switch in the armed position, note the rise of hydraulic pressure to 700 psi, thereby demonstrating that the aux hydraulic pump is operative. If the battery is low, Starting the left engine with the aux hydraulic switch in the off position and turning on the alternator and then energizing the aux hydraulic motor accomplishes the same pre-flight check of the backup hydraulic system without further drawing down the battery. Prior to start, the pilot should exercise the fuel selector valves, listen for the sound of the main valve opening, followed by the simultaneous sounds of the main valve closing and the crossfeed valve opening as the selector is turned to crossfeed. The two simultaneous sounds should again be heard when reselecting the main fuel position. While in crossfeed, the annunciator crossfeed light should illuminate. Checking the operational status of the hydraulic shutoff valve to the right engine and also the bleed air valves is also in order.
Clear the prop.
The pilot should also note an additional rise of 200 to 300 psi on the hydraulic pressure gauge as the right engine is started, indicating proper operation of the engine-driven hydraulic pump. If the operation of gear, flaps, or nose wheel steering causes a substantial bounce of the hydraulic pressure indicator, the pilot should check for a faulty or incompletely charged accumulator. The pilot should also note disappearance of the red low vacuum indicator button upon starting the engine. Retraction of both red indicator buttons after starting one engine most likely indicates a leak in the opposite side pneumatic system check valve. Failure of either check valve can lead to failure of the corresponding pneumatic pump, followed by loss of the pneumatically driven gyros as the remaining pump's output leaks past the check valve and exits in the reverse fashion through the failed pump. At this point, the pilot has also lost de-ice boot operation. With pneumatic check valve failure, the pilot can suffer a pneumatic pump failure without the red warning button appearing. Later, failure of the opposite pump now leaves the pilot with failure of pneumatically driven gyros and de-ice boots, as well as potential cabin depressurization in the face of a slow door seal leak, which cannot be reinflated. Not a good situation when IFR or in-icing. Abnormal pneumatic check valve action should be attended to without delay.
During the starting procedure, you want to be sure that all radios are off. Also, to ensure that the prop sync and autopilot master switch are also off. This will prevent a transient voltage spike from damaging these sensitive units. Starting the engines with the alternators off may also prevent damage to the alternators, which might otherwise try to aid in the starting process and produce more than their 70 amp output limit. A healthy battery, on the other hand, is quite capable of starting both engines without doing damage to itself. In the unlikely event of a total electrical failure, having previously identified several critical circuit breakers which should be left operational helps the pilot in a moment of stress. These include one navcom, one panel light system, the transponder, the door seal, the elevator trim, and the landing gear position indicator. Other breakers may be pulled to conserve battery power. Warming up the engines at the lowest possible RPM cuts down engine wear during the first few moments when the oil is still cold. Alternators do not come fully online at these low RPM settings, but the temporary load demanded from the battery as a consequence is easily handled until RPMs can be increased when oil temps begin to rise.
During the inflation cycle, the normal needle indicator will deflect far to the right and then return quickly to normal. Failure to do so indicates a leak in the pneumatic system and will result in quick destruction of the pneumatic pumps, unless the door seal switch is deactivated and that the aircraft is flown in an unpressurized mode until the leak has been fixed. Alternators can function normally at low output and not reveal a slipping alternator belt or bad diode, which will, however, show up at a heavier output demand, which the alternator will not be able to provide. When checking alternator function, if needed, turn on the landing lights and or other equipment to up to 40 to 50 amps as seen on the amp meter when set in its center position. Push the voltage indicator button to check total bus voltage being created by the alternators. It should be around 28 volts. Now shut off one alternator and turn the ammeter selector switch to the output indication of the other alternator. Ensure that the alternator is indeed putting out the 40 to 50 amps required of it and that the voltage is still maintaining itself at around 28 volts. Repeat the process with the other alternator. Be sure to turn on both alternators when finished and turn off all extra equipment turned on for the test. Finally, compare the amperage output of each alternator. They should be roughly equal. Taxiing the Aerostar with its hydraulic steering brings on its own unique set of demands. Before taxi, perform a 4-point taxi rocker switch check. The pilot should hear no steering solenoid activation nor see any drop in hydraulic pressure, which would indicate nose wheel turning unless both corresponding components of the rocker switch are simultaneously depressed. Pushing the rudder pedals offers no control of the aircraft while taxiing. The 4-point rocker switch located on the center console serves as the primary method of keeping the aircraft on the taxi center line. For tight turns, differential braking and differential power aid the hydraulic steering system. It's very important to set RPMs exactly equal for taxi, typically at about 900 to 1,000 RPMs, depending on weight.
On the ground, certainly shouldn't taxi with the upper door open. Not only is it not safe with the propeller out there, but in addition it can wear the hinges on the upper door, and that's a very expensive item to replace.
Turning while taxiing will cause the fuel in the wings to be displaced towards the outside radius of the turn, with the outside wing fuel gauge showing less fuel than actually exists in the wing, and the inside wing showing more. Both on the ground and in flight, the only time you can accurately read the fuel gauges is when the wings are absolutely level, the ball is centered, and the aircraft is in level pitch. The time the aircraft is taxied out, the engines are warm enough that one or both may fail due to fuel vaporization, as manifold pressure is reduced to stop the aircraft while awaiting clearance. Watch for fluctuating fuel pressures when reducing power below 1,000 RPMs, and be ready to turn on the boost pumps to prevent the engine from shutting down. The same fuel vaporization tendency holds true for operations in flight. Fuel pumps should be left on until in cruise with final power settings. It may take as long as 20 to 30 minutes before the pumps can be shut off without encountering fluctuating fuel pressures. Above higher altitudes, especially with warmer temperatures, it may be necessary to leave the pumps on to avoid excursions in fuel pressure. Naturally, monitor fuel pressures whenever shutting off the fuel pumps. When testing magnetos, ensure that a 50 to 175 RPM drop is obtained when on a single mag operation, and that there is no more than a 50 RPM difference between the two mag drops. Failure to observe any drop on a single mag operation means that the second mag is not grounding out. That is, there's most likely a broken P-lead. This is the wire which runs from the magneto to the magneto selector switch in the cabin. It must be intact to shut off the magneto. If broken, then the pilot will be unable to shut off that mag in flight if it starts to misfire. Further, if the broken P-lead is on the right mag, that is to say, no mag drop is obtained when running on the left mag, the pilot will be unable to restart the engine after shutdown, since normal starting requires the right mag to be grounded out or shut off during starting.
The second type of mag drop problem can be a mag drop of less than 50 RPM. This usually indicates advanced timing of the spark due to point wear in the magneto and predisposes the aircraft engine to detonation and pre-ignition, neither of which is conducive to a safe flight. The magneto needs to be retimed. Don't think, as some unwary pilots do, that a less than 50 RPM drop is somehow good and indicates a stronger or more healthy magneto. A drop of greater than 175 RPM or a difference in the drop between the two mags of more than 50 RPM suggests a bad plug, perhaps from lead fouling, a bad plug lead itself, delayed timing, or internal failure of the magneto itself. If an attempt to lean the fuel mixture to burn off any lead which is potentially fouling a plug is unsuccessful, then return to the hangar for maintenance.
Correct elevator trim for takeoff varies with aircraft loading. Remembering that a rearward CG, due to heavy baggage in the aft compartment, or fuel in the auxiliary tank, mandates only minimal up elevator trim to avoid over-rotation and possible stalling the aircraft at takeoff. Rudder trim should be set slightly to the right for takeoff. Be aware that the Aerostar is very demanding of rudder trim input. Rudder trim is required to center the ball during climb and needs resetting during the cruise and descent portions of the flight. Every time pitch, power, or airspeed is substantially altered, the pilot should check to see that the ball is centered.
Sullivan County traffic, Aerostar 8217 Juliet, taking the active runway 15, departing to the south. Now on the power up, we bring it up to about 30 inches. I'm looking to make sure that the turbochargers are spooling up equally. We line it up either straight on the runway line, in which case we'll bring in an extra 2 or 3 inches on the left side, or as in this case, it's a bit easier to aim about 10 degrees to the right. And then when the power is brought in, the torque will bring the aircraft back nicely towards the center line, and only mild braking is required to adjust the differential steering on that score. We never use the nose wheel steering while on the takeoff roll. We're bringing our power up now to 30 inches, and we're going to check engine parameters. And at 30 inches, our oil pressures, fuel pressures, cylinder head temps look good. Fuel flows are equal, and fuel pressure is good. So and the EGT and the graphic engine monitor looks good. Fuel pumps are on high, and we're ready to go. Aerostar 17J is rolling, runway 15, Sullivan County. So we bring the power up, release the brakes, and we go right down the center line. This is just working out perfectly. We're up to red line now, and okay, attention's directed now to the runway, coming through 60 knots. We'll rotate at about 90 knots. We're coming through 80, and here comes the rotation.
And we're through 100 knots, gears coming up.
We're going through 110 knots. At about 120 is a good time to raise the flaps or blue lines about right. You don't get a sinking sensation when you do that. And we're now through 120, and we're climbing out nicely. We're locking our flap selector in neutral to avoid any loss of hydraulic pressure should we suffer a failure of that system.
When heavily loaded, raising the flaps 10 degrees at a time and allowing the aircraft to accelerate to 130 knots before removing the last 10 degrees of flaps seems to work well. Reducing manifold pressure and RPM for cruise climb at 1,000 feet offers a quieter ride and better engine cooling. For all the Aerostar models, lowering the nose from best rate of climb speed to anywhere from 130 to 160 knots, depending upon the particular model, increases over-the-nose visibility, aids engine cooling, and only marginally cuts rate of climb. Lowering the nose while accelerating from blue line to cruise climb is initially accompanied by a marked decrease in rate of climb. But as airspeed increases over the laminar flow wings, lift increases also. By the time cruise climb speed is achieved, rate of climb will have returned to a quite satisfying indication. During initial climb, after manually synchronizing the props, engage the electric prop sync, which will take over the task of harmonizing the props. Trimming rudder and ailerons as required makes for a more comfortable and aerodynamically efficient climb. The Aerostar pressurization system is conventional in all respects. For smooth and more comfortable cabin pressurization control, adjust the cabin controller before takeoff to begin pressurization 1,000 feet above departure airport elevation. After the cabin is pressurized, rotate the outer ring clockwise to planned cruise altitude plus 500 feet, thereby selecting the lowest cabin altitude which can be maintained without pressure spikes when moving the throttles. Before descent, rotate the outer ring counterclockwise to select a cabin pressurization altitude of 1,000 to 2,000 feet above destination airport. Selecting too low an altitude for cabin depressurization results in the cabin altitude rising when power is reduced in the airport vicinity prior to landing. Leaving the rate controller in the neutral position results in comfortable rates of cabin pressurization change. When approaching cruise altitude, commencing the level off a few hundred feet in advance allows for a smooth transition to level flight. Do not level off by dropping the nose completely to the horizon. Doing so will have the aircraft descending below the desired cruise altitude. Instead, drop the nose to a slightly nose-high attitude and allow the airspeed to build towards the anticipated indicated cruise speed. As the speed increases, more lift will be generated by the wings, and while holding desired cruise altitude, the nose can gradually be dropped to its final attitude as anticipated indicated cruise speed is achieved. 1650 degrees EGT is redline maximum operational temperature. EGT gauges often are miscalibrated. Only one of the two exhaust stacks is temperature monitored, and the other may well be running hotter. To allow for these variables, it would seem wise to limit leaning to 1600 as a maximum operating temperature. At 75% power, the turbocharged Aerostar, especially the higher powered models, will peak out at over 1700 degrees during leaning, which could damage various exhaust components exposed to such temperatures. Simply leaning to 1550 and stopping there offers safe operating temperatures and ensures that the engine is running well on the rich side of peak. On stock 601P models without the cooling kit, leaning should be to specific recommended fuel flows rather than to EGT indications. Confirm that fuel flows are as anticipated after the leaning process with all Aerostar models. For both stock Aerostars with the cooling kit and Mach-in modified machines, running at lower power settings, it may well be possible to lean peak below 1650 and then enrich in at least 50 degrees while always ensuring that the resultant operating temperature is at 1600 degrees or below. Using the Autopilot in cruise relieves pilot workload and allows the pilot to monitor aircraft systems and changing weather patterns. With or without the Autopilot, however, the aircraft must be trimmed for straight and level flight, both for aerodynamic efficiency and to avoid wing fuel imbalance. One wing low and using opposite rudder to maintain a constant heading results in more fuel being consumed from the higher wing tank due to a greater head of pressure. Paradoxically, the fuel gauge will erroneously indicate more fuel in that wing because the fuel sensor is located at the inboard extreme end of the tank, and the elevated wing displaces the remaining fuel in the disproportionate amount to the inboard wing area where the fuel sensor is located. To avoid both unequal wing tank fuel and the associated fuel gauge deception, fly with the wings level and the ball centered. Trim out any tendency for a wing to drop with aileron trim if installed. If not, cross-feed fuel until the wings stay level without any control wheel pressures. Turn the fuel selector to the right on the wing side that's light. Tells the pilot which fuel selector to place in crossfeed and direction in which to turn.
Do not fall into the trap of turning the right fuel selector to the left in order to crossfeed from the left wing. A silent right engine will be the result of that unthinking maneuver.
Trimming the rudder can affect aileron trim and vice versa, so recheck each for final trim adjustment after the first gross adjustments are made. If the Autopilot is engaged with one wing heavy with fuel and opposite rudder trim set to hold a constant heading, the Autopilot will allow this aerodynamically inefficient attitude to persist. The Autopilot controls heading by aileron input and altitude with elevator input. There is no Autopilot rudder input. In cruise, occasionally disconnect the prop sync for a minute or so, allowing the slaving unit to recenter itself. This will prevent the slaving unit from reaching the end of its travel, causing the props to shift out of sync. With the Sentry Autopilot, which is standard equipment with the Aerostar, when the pitch sync or control wheel steering button on the right side of the yoke is depressed, the pilot may hand fly the aircraft until the button is released. When the button is released, it's important to remember that the Autopilot will have switched from altitude hold to attitude hold mode. The aircraft can now gain or lose altitude depending upon what attitude the aircraft was in when the pitch sync button was released. After pushing the left yoke button, both the Autopilot off-on button and the altitude hold button must be re-engaged to resume full function. When releasing the pitch sync or control wheel steering button, only the altitude hold function must be re-engaged. Routine descent in the Aerostar from altitude requires some attention to detail not required to the same degree in other twins. As airspeed builds in the descent, left rudder trim will be required to keep the ball centered and the aircraft fuselage in line with the slipstream. For those aircraft which do not have a small rubber strip installed in front of each main gear door to deflect the airstream away from the front edge of the door, a popping sound may be heard at higher airspeeds during descent. This is the result of high-speed air sneaking in between the fuselage and the door, pulling it open a bit. The door will intermittently slam shut with a rather loud bang. Reducing the indicated airspeed will solve the problem. Also, during descent, watch for ram air spinning the turbos faster and increasing the manifold pressure beyond that desired. Be ready to throttle back a bit. This will normally occur when above the critical operating altitude of the turbocharger system, with the wastegate fully closed and unable to modulate manifold pressure. Upon starting descent, the pressurization controller should be set with a counterclockwise rotation to select an altitude 1,000 to 2,000 feet above the destination airport. Approaching this selected altitude for cabin depressurization, the check valve in the tail air duct will be blown open by ram air pressure, often with a fluttering sound heard within the cabin. Confirmation of this event can be had by seeing that the cabin altitude now matches aircraft altitude. If the aircraft is in a high-speed descent when the check valve opens, the cabin rate of climb will show a sudden descent for a few moments as the incoming ram air briefly pressurizes the cabin before the outflow valve can compensate for this effect. Reducing power and selecting flaps 20 degrees below 174 knots allows the aircraft to slow to below gear extension speed of 156 knots. The prudent pilot will try to slow considerably more than that, however, before lowering the landing gear. Airspeed puts high stress on the landing gear strut doors, and they're subject to cracks and failure at the attachment hinges. Planning the approach to lower the gear at or near blue line will be potentially less injurious to these doors and therefore less injurious to the owner's wallet. Similarly, lowering the landing gear when the aircraft is in somewhat of a slip or a skid puts side load forces on the main gear clamshell doors, which can break the so-called banana bell crank in the main gear door actuating linkage. For that reason, it's wise to only lower the gear when flying straight and level. If not, at the very least, make sure the ball portion of the turn and bank is centered in its race when deploying the gear if in a turn. Do not release the gear handle until confirming 3 green lights. If there's a question of gear position, the main gear can be seen by looking out the window on either side, and the nose gear position confirmed by the spinner reflection. Shutting off the prop sync and air conditioner on short final primes the aircraft for go-around, should such be required. Holding blue line speed on final until landing is assured, followed by extending full flaps and reducing to over the number speed of about 100 knots if heavily loaded and 90 knots if lightly loaded, seems to work out well. To aid in a stabilized approach, some pilots prefer final flap deployment at 1,000 feet above the airport when IMC and 500 feet when VMC, realizing that an engine failure at this point still allows them time to raise flaps to 20 degrees and continue the approach for a single-engine landing. Remember that except for the Piper 700P, the Aerostar has no stall warning horn. There's a rather pronounced aerodynamic buffet when near the stall envelope of the aircraft, but the pilot is well advised when maneuvering for landing and when coming over the numbers to pay particular attention to airspeed. Carrying some power, which is gradually reduced throughout the landing flare, allows for a smooth touchdown. Do not chop the power suddenly during the flare, but carry a bit of ever-decreasing power throughout the landing until the wheels are on. The aircraft, having a heavy wing loading, will impact the runway with a great deal of force unless a bit of power is maintained as described. The landing attitude should not be excessively nose-high, and the nose wheel should be gently lowered to the runway, while elevator control still maintains authority. During the rollout, after the nose wheel has touched down, up elevator should be employed to unload the nose wheel, as was done on the takeoff roll. Heavy braking, when not required, only shortens the life of the brake pads and drives the nose wheel forcibly onto the runway. If the landing lights were on for landing, shut off one of the lights to avoid excessive heat buildup and consequent crazing of the landing light plexiglass cover. Identify the flap handle and raise the flaps after exiting the runway. Note the time and allow at least an additional 2 minutes for the turbos to both slow down and cool down while there's still engine oil circulating through the turbocharger bearings. Otherwise, when the engine stops, the engine-driven oil pump is no longer functioning, and the turbocharger will be spinning on unlubricated bearings, which is not conducive to long turbocharger life. Recheck that the heater has cooled down before shutting off the master. Briefly, shut off each mag, watching for RPM drop towards zero, indicating that both mags on the particular engine are grounded out and that there is no broken P-lead to prevent the next engine start, or worse, to injure someone who gets too near a live prop. Before shutdown, be sure to deactivate the door seal pressurization switch. It takes 5 to 10 seconds for the door seal to deflate. Do not force the door open with a partially deflated seal. That risks damaging the seal. Rather wait until the seal is fully deflated before opening the door. After shutdown, be sure that all the mags, fuel selectors, fuel pumps, and alternators are off. Leave the individual cabin light switches always in the on position, allowing the pilot to control their operation from the rocker panel switch. Leaving the lights on at night for exiting passengers is a mandatory safety procedure given the small step upon which to exit. If several minutes will elapse while unloading the cabin, consider pulling the turn and bank electric motor circuit breaker along with the electric backup attitude indicator if such is installed to avoid running the battery down. Lastly, after turning off the cabin lights, be sure to shut off the battery master so that you can fly on another day. To prevent an inadvertent dead battery, some pilots leave their strobe light switches on all the time to prevent their walking away from the aircraft
with the battery rocker
in the on position. Finally, a quick post-flight inspection for major oil leaks around the integrity of the aircraft might allow for detection and repair of a problem before the next flight, rather than having to cancel at the last minute when the problem is then discovered.
Well, there you have it. Flying the Aerostar, the fastest piston twin in the world. To do it safely, you need proper initial ground school and flight instruction. Simulator training is a great help, especially in handling single-engine emergencies. We didn't cover any emergencies in this video, so studying your operating manual and practicing with Aerostar knowledgeable people is absolutely mandatory. Don't forget that the AOA can be a great source of information regarding the care and feeding of your aircraft. We hope that this video, while no means being complete, does aid you in your goal of being the safest Aerostar pilot you can be. This is Ken Wolf wishing you on behalf of myself and the Aerostar Owners Association happy, safe, and speedy flying.